Hello, everybody. My name is Ethan Foss. I work with the Space Rendezvous Lab at Stanford University with Professor Simone D'Amico. And today I'll be presenting some research related to long-duration station keeping strategies for cislunar spacecraft formations. So to start by motivating the problem for cislunar formation flight, it's important to consider the push towards greater presence in cislunar space. With the Artemis mission and new Gateway space station, which are the Gateway is supposed to operate in a 9 to 2 NRHO about the moon. Technologies relating to rendezvous, proximity operation, and docking must be extended to the cislunar regime. Moreover, the paradigm of distributed space systems opens a lot of doors for advanced mission strategies and also enables further automation. So to sort of motivate what the challenges are of cislunar space and why we can't just, take the technologies that are readily available for low Earth orbit, we consider some challenges related to cislunar formation flight. First of all, cislunar space is fundamentally chaotic, unstable, and sensitive, which makes things really challenging for GNNC. Also, navigation error is quite a bit larger in cislunar space. For example, the 9 to 2 NRHO has an orbital plane that's nearly perpendicular to the line of sight to the Earth, and this leads to greater error in navigation. And lastly, and fundamentally, general and exact analytical solutions have not been found for three-body motion. And this presents a lot of challenges related to generating analytical solutions to relative motion and describing periodicity in the regime. So talking a little bit more about some of the prior work that's been done here. So there's a lot of growing interest in cislunar space, and so there's a strong corpus on cislunar formation flight. However, a lot of these works have a lot of fundamental limitations that need to be addressed. First of all, a lot of this work works under idealized assumptions, so lower fidelity models, perfect state knowledge, no uncertainty. They also typically only consider short durations of formation flight. Oftentimes, there's little or no considerations for passive safety, and the algorithmic frameworks typically do not scale very well with agent count. So we seek to address some of these limitations in this work by considering these realistic conditions. So we simulate in a high fidelity environment, we have realistic navigation errors, and we incorporate misthrust events. And our strategy is also validated on long duration formation flight. We also introduce a novel technique for efficient handling of passive safety, and the resulting GNNC framework is highly modular and scalable. So to give a bit more background on cislunar space and the dynamics behind it, we'll first consider the absolute motion. So this work in particular will leverage the CR3BP and high fidelity ephemeris model. This motion is typically described in a rotating frame about the Earth moon. Our ephemeris model is going to consider Sun, Earth, and Moon perturbations, gravitational perturbations, and sometimes SRP. And our strategy for generating relative motion in this case simply relies on numerical propagation of state transition matrices. So by taking first order approximations about a reference absolute trajectory, we can generate these relative motion models. And another important aspect is the reference frame that we consider. So for our chief reference frame, we work in a velocity normal binormal frame, which is quite popular in deep space applications. And essentially what we have are the axes aligned with the velocity of the chief, the normal, so it's taken with respect to the moon, and then the binormal to complete the triad. And to give a bit more background into how relative motion is generated in cislunar, let's first consider how this is done in the restricted two-body problem, so the problem that most of us are very familiar with. Fundamentally, periodic solution are all states with eccentricity less than 1 in the restricted two-body problem are periodic. So generating relative motion can be thought of as finding a neighboring absolute trajectory. If we look at the state transition matrix over one period of a given orbit, we see that the eigenvalues correspond to 1. All of the eigenvalues are on 1. And so what this means is that all relative trajectories can be represented by a combination of eigenvectors associated with the non-degenerate eigenvectors of the state transition matrix. This is sort of maybe a confusing way of thinking about generating periodic motion, but it becomes a little more clear when we consider cislunar. So for example, if we consider a 9-2 NRHO in the CR3BP, which admits periodic solutions, we see that the state transition matrix over one period admits 2 central modes. So these are modes that are on the unit circle and have real and imaginary components. And what happens is if you perturb these modes, you create what is called a quasi-periodic orbit. And so this is a neighboring structure about the underlying periodic orbit, which admits trajectories that lie on an invariant torus. So if we look at these, this orbit in the chief frame, we can see we generate this relative motion with these interesting structures here. So with that established, what's the challenge with doing GNNC exactly? Well, there's a couple problems. First of all, the dynamics. So the dynamical model error between the CR3BP and an ephemeris model or a truth model is much larger than what you would typically see in the restricted two-body problem. And this is because, one, the fundamental solution of circularity of the Earth-Moon system is pretty off, as the orbit of the Moon about the Earth is non-negligibly eccentric and wobbling. Also, the relative perturbations with respect to the strength of the gravitational attractions of the primaries. In Leo, you would see that the perturbations are much smaller than the gravitational attraction of the Earth. Whereas in like the 9-2 NRHO regime, these perturbations are relatively much stronger. So this affects the orbital motion a lot. And we can see this by simply taking a periodic orbit in the CR3BP and propagating it in a high fidelity ephemeris model. And we'll see that it diverges in just a few orbits. So this is obviously a problem and a challenge for cislunar GNNC. Second part, which we sort of already touched on, is the instability. So the plots associated, or the eigenstructure associated with the 9-2 NRHO, for example, admits stable and unstable modes, which means that any point that is on one of these trajectories will fundamentally fall off it with the accumulation of error. This means that we have to do station keeping quite frequently. You can contrast this to the restricted two-body problem, where trajectories at worst diverge at a linear rate, since the geometric multiplicity of the eigenvalue is 5, I think. Yeah. And then lastly, safety. We can sort of conceptualize why safety is so challenging just by looking at the eigenstructure itself. In the CR3BP, the eigenvectors corresponding to this unstable and stable modes are constantly changing in time, which means we cannot position our spacecraft in such a way to avoid these modes necessarily. Whereas in the restricted two-body problem, the unstable mode operates along the tangential direction. So as long as we can avoid configurations where two spacecraft are crossing in those configurations, we can guarantee safety. So one way to sort of imagine why safety is more challenging is by simply looking at how much delta V it would take to drive a spacecraft to an unsafe state. And the CR3BP for the 9-2 NRHO for kilometer level separations is just 3 millimeters per second to drive your spacecraft to the origin. Whereas for the restricted two-body problem, it takes about 300 millimeters per second. So with these challenges established, let's go through how we can take each of these challenges and address them and approach a modular GNNC framework. So the first step is to produce reference trajectories. So ephemeris models don't admit periodic solutions. So the way we take care of this is by transitioning an underlying periodic orbit in the CR3BP into an ephemeris model using shooting techniques. And when we do this, we can produce long duration absolute trajectories in a high quality model. And then to generate the relative motion, since the CR3BP admits periodic solutions and the ephemeris doesn't, we have to make a few compromises to get this relative motion. So you can see the eigenstructure of the ephemeris about this 9 to 2 reference is quite similar to the CR3BP, but we'll notice that the eigenvalues are like slightly perturbed from the CR3BP. What this means is we can't generate bounded relative motion for infinite durations. But if we perturb these eigenvalues, we can still obtain a quasi-periodic relative orbit for sufficient durations to be useful. So to see this more, we can see how at various revolution counts by taking the eigensystem at each revolution and producing the corresponding quasi-periodic relative orbits, we can still obtain useful relative orbital geometry that can be leveraged by the scheme. So for 1 revolution and 3 revolutions, we have favorable geometry, and we can see that the separations are pretty good. So this is the separation from the origin of the system, so from the chief. And then as we see, when we increase these revolutions count, the geometry tends to degrade a bit. But we find that using 12 revolutions is a good sweet spot. It offers like a good compromise between minimizing the separation ranges that the spacecraft will encounter and also the periodicity at which the underlying orbit will need to be switched. So with this reference generation technique established, let's see how now we can leverage these concepts to produce a modular GNNC architecture. So the way we'll do this is taking our state estimates from our estimation, we can produce a virtual chief and also produce the relative states associated with that virtual chief. The virtual chief can be used to compute an absolute control law to drive the formation to the reference NRHO. And then the relative states can be used to derive a relative control law that drives the formation to the desired geometry about these quasi-periodic relative orbits. Then we can just sum these delta V's. The problem is, though, that none of these schemes inherently consider passive safety. So to do this, we introduce a control barrier function safety filter to take these nominal maneuver magnitudes and make them safe. So to dive into this a bit further, let's first consider the maneuver placement. So where along the orbit we want to make maneuvers. And we found that placing absolute maneuvers at a true anomaly corresponding to 160 degrees tends to work pretty well. Generally, you want to do maneuvers near apolune because that corresponds to the least sensitive region of the orbit. So errors from your maneuver execution error and navigation will not propagate as significantly at this region of space. And then generally, we want to do relative maneuvers after we do this absolute maneuver to clean up for any errors as we enter the periapsis crossing. So this is what a typical strategy would look like. Perform an absolute and relative maneuver at a true anomaly 160 degrees, and then perform a relative maneuver at 200 degrees. And then to choose the virtual chief, a naive strategy would be to just choose one of the spacecraft as the chief. However, this doesn't work super well because what that means is the relative station keeping burden of that spacecraft will be non-existent. Whereas if we use like an averaging strategy, which chooses a virtual chief to minimize the distance of the formation geometry to the true geometry, then we allocate station keeping burden evenly among the agents. So the way we implement this in absolute control law is similar to state-of-the-art approaches. And we just use a nonlinear MPC strategy that targets a periapsis crossing 6 revolutions in advance. This strategy has been found to produce very good delta V expenditures. And then for our recursive targeting law for the relative maneuvers, we simply take the relative motion generated about the absolute reference trajectory and use that to compute a delta V that will drive the relative trajectory to its reference. So it's a simple linear targeting law. And then for the safety concept, we introduce a control barrier function. So these are used frequently in robotics contexts, and essentially what they do is they involve filtering a nominal control input to keep your system safe. And this allows for modularity in the approaches of the control architecture. So in particular, we avoid having to impose safety in combination with an absolute and relative control law by simply computing those individually and then applying the control barrier function afterwards. And to make our formulation amenable to using a control barrier function, we make some assumptions. First of all, we assume that the propulsion cutoff duration is bounded, and we assume that following a cutoff, the agent will not miss a maneuver at its next opportunity. So if we do this, we can enforce stochastic keep-out zones for a duration of the following trajectory, and then leverage semi-infinite programming approaches to efficiently solve this problem to guarantee safety while also including a modular approach to the GNNC. So to demonstrate this strategy, we implement the following simulation protocol. So we have EKF implemented with that uses deep space network ranging and intersatellite ranging. For control, we apply mismaneuver events and control execution error. In the dynamics, we inject random SRP accelerations, and we validate the approach on a couple scenarios. So first, like a 2-agent scenario with around 10 kilometers separation, a 5-agent scenario with around 1 kilometer separation, and a 9-agent scenario with around 100 kilometer separation. And then we do several Monte Carlo trials to validate the proposed approach. The metrics that we're interested in are the delta V expenditure. So we can see that the approach, when simulated, produces delta V expenditures on the range of 10 centimeters per second for one agent for 1 year. And this is very favorable and not much more expensive than you would get for a single spacecraft mission doing its own station keeping. And we can see the relative separation ranges are a bit large. So for example, in the 2-agent scenario, we see ranges of separation from like 1 kilometers, which is quite a bit. But this is sort of the nature of Cislunar and how the Cislunar geometry expands at perilune. And then finally, we can see that the computation times are very favorable. The most expensive procedure is computing the absolute maneuver. And computing relative maneuvers and the control barrier function computations are very minimal in comparison to the absolute maneuver scheme. So to visualize this, we can see the 2-agent and 9-agent approaches. So you'll see the characteristic shape of the quasi-periodic relative motion in the top figures. And you see that the stretching of the invariant circles at periapsis crossing. Moreover, you can see where we're actually making the maneuvers. So we make the maneuvers at 160 and 200 degrees of true anomaly. And these figures here sort of demonstrate, I guess you can't see, but this figure here is sort of a quantification of our tracking error, or the extent to which we're succeeding in retaining our formation geometry. And you can see there's quite a bit of error, particularly at perilune passing. And this is mostly due to the fact that our linear dynamics, or the linear dynamics used to generate the reference trajectories, is less valid at perilune as a result of absolute dispersions from the absolute reference trajectory. So, and then we can also take a look at the 5-agent demonstration, which features the smallest separations. So the separations here are on the order of kilometers and can even get to as low as hundreds of meters. And this is a particularly useful demonstration because it features the most activations of the control barrier function. So what that means is the control barrier function is detecting unsafe maneuvers, And when it does that, it runs an optimization routine to filter these maneuvers. Um, so as you can imagine, when the formation has a much tighter geometry, to enforce safety, it will encounter many more unsafe proposed maneuvers. So we can see that in a naive approach, when no CBF is applied, on the top plot, we see that following a mismaneuver, two spacecraft come to within 30 meters of each other, which is a very unsafe condition. However, when the CBF is applied, when this mismaneuver occurs, uh, the CBF automatically makes these maneuvers safe. And we can see that the minimum separation distance is on the order of hundreds of meters now, which is the prescribed bound. So we can see that the CBF is working successfully. And moreover, it's not introducing a lot of additional burden in that it's only applying optimization schemes when it needs to. So in conclusion, we demonstrated the extension of quasi-periodic relative orbits to high-fidelity dynamics. We introduced a complete scalable modular GNC architecture for formation flight for high-fidelity scenarios in cislunar space. And we also introduced a novel technique for enforcing passive safety in cislunar. Future work will focus on demonstrating the strategy on other orbital regimes of interest, including advanced reconfiguration strategies for phase swapping, QPRO switching, things like that. And we'll also look into further study of strategies for generating long-duration quasi-periodic relative orbits. So with that, I'll take any questions. Thank you.